This demonstration will show an interesting approach to solving a basic contact problem. The model simulates the use of set screws to maintain a pin in its retainer. An end load on the pin is trying to extract the pin from the retainer. We are trying to evaluate the integrity of the set screw's retention with respect to the operating loads. At what point will the pin begin to slide out from under the set screws? The ability of the set screws to retain the pin is driven by contact forces. Let's take a look at the model. The model is composed of three basic components. Set screws, both in X and Y directions of this model. And then there's a shaft. So the shaft is broken up into two pieces, a primary body and then the shaft or pin, as I'll probably refer to it as well, in the contact zone. And then we have a retainer, the retainer main body and the retainer portion in the contact zone. If I look at the solid meshes, they're kind of related to those bodies. I have, again, the shaft, and it is composed of two meshes, one in the contact zone, and it has a finer element size, finer mesh size compared to the rest of the body. Similarly, we have mesh for the roller or retainer. It's got a finer size in the contact zone, and then we have set screws themselves. Of note is maybe that the geometry of the pin has a diameter slightly smaller than that of the retainer, so it fits in nicely without an exact size of the hole that it's retained in, and the surfaces of the set screws match exactly that of the pin. So this was a geometry simplification of those set screws. Next, we're going to take a look at the end of the pin, and we have a spring element and a constraint on the free end. This is done so that the extraction load is not applied directly to the pin. Doing so would cause the pin to slide almost immediately, and that would underestimate the force required to extract the pin. So if we take a look at the meshes there, we have 1D meshes for a constraint element that's sliding from a point to the nodes on the free end of the pin. And then we also have a C-bush element. So this is shown there. It's going between 2 points, and it has a primary stiffness defined in the axial direction. So if I do an information on this, you can see the stiffnesses related to the X, Y, and Z directions in the global coordinate system. It has a stiffness in the Z direction consistent with the stiffness of the pin, and then it has a very small stiffness in the X and Y directions, which really aren't of any interest in our analysis. Next, we will review the contact, constraints, and loads in the model. First, let's review the contact setup. There are 2 contact pairs and 3 contact regions. Friction is defined in both contact pairs. So let's scroll down to our solution. We can expand our simulation objects. We see 2 contact pairs. First being that between the retainer and the pin. If I edit that, I can see the source region as the retainer and the target region as the pin. And we have a coefficient of friction defined with an expression. So I did this in order to drive both contact pair friction settings with a single value. So that's an expression, and if I cancel here, I can go into my expressions and then look at here friction. I can change that value here, and that will apply to both contact pairs. So next I will go into the second pair and just edit this and see that it's also using the same pin region, and then in this time it's contacting with respect to the set screws. And we had the same contact coefficient of friction using that expression. Now let's review the constraints. They are sufficiently defined to prevent rigid body motion and focus attention on the axial behavior of the model. So if I expand the constraints in the solution, we see we start with a fixed roller constraint on the back end of the retainer. Then we also have constraints defined on the set screws. So these are cylindrical constraints in those local cylindrical coordinate systems, just to prevent, say, transverse displacement of the set screws. And then we also have a fixed shaft constraint. It's really a constraint on the free end of the spring. So again, we're not concerned with how that point is displacing transverse to the pin axis. So we put a constraint there on the end. First load in the model is that of the axial loads applied to the set screws. These loads initiate contact and are held fixed through the duration of the solution. They generate the friction forces that keep the pin in the retainer. So I'll turn on the display of those two set screw forces, and I'll edit one of them. You can see it's applied to the top surface of that set screw, and its direction is parallel to the axis of that set screw, and it's using an expression for its magnitude. So if I look at that expression, I've got it set to a certain value, and that means that this force is it's not varying with time, but when we apply it in the first step, we're going to, by default, ramp it from a value of 0 up to its constant value, and then it becomes held fixed in subsequent steps of the solution. The second one is defined in the same manner, using that same expression, and then the direction is just applicable to its set screw axis. The second load in the model is an enforced displacement in the anaxial direction of the pin. It uses a linear ramp over time, and Simcenter Navtran can treat enforced displacements as constraints or loads. However, it also supports enforced velocities and accelerations only as loads. And this is where the UI in Simcenter 3D can be a bit confusing. But first, let's take a look at how the load is defined in this model. So in my loads container, I have an enforced axial displacement. Let's see if I turn that on. It's showing a force applied to the free end of the spring. And if I modify or edit this one, it's saying I'm an enforced motion load and I'm applied to DOF3. So this is the Z translation in that global coordinate system. Now the transient excitation set is where we have an enforced, a transient field defined. So the excitation and the control of that enforced motion over time is specified in this field. And we can see from the table it's held at a value of 0 for the first second. This is when our set screw loads are being applied. And then after time 1 onwards, we're just linearly ramping that enforced displacement. And now the confusing part is that we have an enforced displacement constraint and also an enforced motion load. So again, this difference here is that we can have accelerations or velocities defined as a load. We can only have enforced displacement constraints in the constraints specification. My loads are all at the global level, meaning that they are all active during all steps of the solution. But I define the solution with 2 basic steps to control time stepping and post-processing. The first step relates to the axial loads on the set screws, and this has an end time of 1 second, and it is completed in 2 iterations. So we can take a look at our steps. If we look at our subcases, we have screw force and shaft extraction. That first step has an end time of 1 second, and it's applying the load in 2 increments. So in the first step, it'll have the set screw loads. They'll have half their magnitude, and then in the second step, they'll have their full magnitude And then from that point onwards, those magnitudes will be constant. And then we have shaft extraction as a second step. And this step has an end time of 1.2 seconds, and it has many more increments. It has so many more increments in order to adequately capture the onset of sliding between the pin, retainer, and the set screws. Now let's take a look at some of the results. First, I want to review the contact status. It will indicate where contact is open, closed, or sliding. So go to my post navigator and find my contact status results, do a contour plot, and it basically has three values. A value of 0 indicates the contact is open, a value of 1 indicates contact is closed, and a value of 2 indicates contact is sliding. Now I prefer to look at these results using spheres. The default sphere size is a bit large, so I'm going to scale that down to 0.2, and I'm not going to size it by result just by having every value scaled. So I get a sphere drawn at every location where there's contact, and then I can animate across iterations to see how that contact is evolving over time. So we see closed contacts, and then they go to sliding. So green being closed, red being sliding, blue being open. And again, initially we are closed for the most part, and then as that enforced displacement takes over, the pin starts to slide out. If I pause that and then go back to a point where I want to try to identify where the contact is transitioning entirely to sliding, and it's around this point, so 1.07, around 1.07, 1.08 time frame is where we get sliding entirely occurring. I also have there's a nodal force report. If I look at this, I can get a graph of reaction force or any of my other type of forces. So here I've got reaction force on that one point or node that has the enforced displacement. And so then from here, I can generate a graph. So I'll create those graphs across iterations for my forces. And I can plot the Z component of that in a new window. And we see the evolution of the reaction force. So from 0 to 1 second, there's no reaction force, because that's when we have our magnitude set to 0, and then we start linearly ramping up our enforced displacement. And if I look at this, we see many time steps along that ramp, but eventually it peaks out and remains essentially constant from one point on this curve onwards, and this is where we are sliding completely out of the retainer. So contact has been overcome at this point. So we can say for this condition at V8 newtons, we are sliding entirely out of that retainer. As a final step, I want to look at results from 3 solutions. And the aspect of the model that changes between these solutions is the scale of the set screwed loads. Let's see how that was addressed. So I'll close that and go back into the standard view of the model, and go back to Simulation Navigator, and we see we have 3 solutions, basically 401.1, 2, and 3. I want to go to my subcase manager in this first solution, and you can see that I've got scale factors set on my set screw X force and set screw Y force. The value is 0.4 for that first solution. And then I go into my second solution, make that active, and it's subcase. And we see that the set screw X and Y force scale factor is set to 1. And then in the last solution, make that active and do a review of its subcases and the scale factor on those two are set to 1.2. So now we'll go ahead and generate our graphs from our notable force reports for both of those solutions. Let's see, I think I have to make that active, and then create graph across iterations, and for forces, say OK. Same thing for the third solution. Create graph across iteration, force, and OK. And I'm going to generate a graph for all three of those Z reaction force. So I think I need to just say generate a plot, and then I'll do an overlay of the subsequent solutions. So I can say, for example, scroll this over and do an overlay on that window and do another overlay of the third result set. And you can see here from the first to the last, I'm increasing that set screw force. So the friction load is increasing as we go from the first solution to the second and to the third. And then we can see from our probe of this content that, at the first one, we're sliding at a value of, say, 48 newtons. At the second one, we're sliding around a value of 120. And then in the third solution, we're sliding at a value of 145. So yeah, the contact and the friction and the application of the set screw loads are all working in combination to give us different answers under these different conditions.